that everyone for today? Okay, let's get started. Good afternoon, everyone. Hello, welcome back. We're in the middle of our polyhedra projects. And as promised, I have an example project to share with you today so you can see a final result of what the expectations are. So you can see everything all together. There's all the parts put together for you to compare. And then we can spend the rest of the time in your groups, and you can get to work. Okay? So then let me put this here. And we'll switch to, actually, let's do this. There you can see the whole thing. All right, so I put together a quick sample presentation on Archimedean solids. You guys read about those over the weekend, so I don't overlap with anybody's actual project here. And this is something I put together in probably less than an hour, all said. Just to give you an idea of the amount of time it takes, it's not that long. It's not designed to be a long, super in-depth kind of project. We're just going to get an overview, a feel for what are these different types of 3D figures here. Okay. Now, of course, you're working together. You're spread out across multiple days. I don't expect that total time it might take you a little longer. That's fine. And I think it came out pretty nice. Okay, I just used a basic theme there. I put in a few extra pictures. Okay, make it look good. Spend a little more time. Add stuff to it, right? You get extra points for creativity here. So make it look as good as you can. All right, find my controls. There we go. So Archimedean solids, what are they? Well, formally, the definition would say that an Archimedean solid is any convex, uniform polyhedron composed of regular polygons meeting at identical vertices, excluding the Platonic solids, prisms, and antiprisms. So those three groups actually meet the other requirements, but we've decided since they have their own categories already, as identified, we'll say the rest of them that meet this criteria are now the Archimedean solids. So what does that actually mean? In layman's terms, right? These are the 3D shapes, no funky crisscrosses or dents, made of 2 or more matching polygons, okay? And where no point looks any different from the other points, right? So you can look at this point right here, or you can look over there, or over there, right? All of the points look the same, right? There's not a definite, this must be the top, this can be the bottom. You can't tell. You turn it upside down, and it looks exactly the same. All right, how can you identify these easily? Spot them a mile away. Here it is. They're pretty much ball-shaped in general, so not some kind of can or a tube like the prisms and antiprisms. And very symmetrical. These are some of the most symmetrical shapes in that you can rotate them around 360 in 3D and get a similar view all the way around. And they are, all of them are made of only 2 or 3 regular polygons. So if you spot any other shapes, you know, 4 or more polygons or irregular polygons, it's not an Archimedes solid. And then finally, there's only a finite list. Just like the Platonic solids only had exactly 5, there's exactly 13 of these guys. If it's not on the list, it's not an Archimedes solid. So that's a very easy way to identify them. All right, here are a few more examples. Ones that we haven't seen on the slide so far. So this one is the truncated icosahedron. Here we have the rhombicosadodecahedron and the truncated icosadodecahedron. Okay? And notice again, they're still holding that rule of this has 1, 2, 3 different regular polygons, and every corner has one of each of those. So I've got red, blue, and yellow. Here, this corner has a red, blue, and yellow. And down here, we can say a red, blue, and yellow, right? All coming together. Every vertex is the same. Some non-examples, right? Some things that would fail that test. Pentagonal prism. It fits all of the criteria as far as regular polygons and all the same polygons at each vertex, but our definition of Archimedean solids specifically excludes the prisms, so we can't include that guy. And here we have a square pyramid, which is made of two different regular polygons. We got triangles up top and a square down here. But because the one vertex, called the apex on our pyramid, is distinguishable from the others, that is, we can tell that this is the top because it's all triangles coming together. Whereas down here we have two triangles and a square, or over here is two triangles and a square. They're different from the one up here. The fact that I can orient this meaningfully tells us it cannot be an Archimedean solid. How about Eulers Formula? Does that hold true for Archimedean solids? Well, let's test one. We'll take the truncated icosahedron seen here as our example. This guy has 32 faces, 90 edges, and 60 vertices. No, I did not count them by hand. I looked it up. That's okay, you can do that. And here is Eulers' formula, just as a reminder. Slightly different format that we've seen before. They moved the 2 onto the side by itself. That's okay. So let's check. Plug in the numbers there. We get 60 minus 90 plus 32 equals 2. Is that true? Well, 60 minus 90 is negative 30. Negative 30 plus positive 32 gives us 2 equals 2. Check. Yes, it works. So that's all you need for the Eulers formula part. Pick one from your category and count and check the formula. That's all you need there. And then finally, a couple historical facts. I put 2 on here. Again, you only really need 1 for your project. These are named after the Greek mathematician Archimedes, okay? Because he was the first guy to list them all together and identify, like, hey, these shapes should go together. They form a group here. You might know him from some of his other famous works, the Archimedes principle, having to do with buoyancy and volume and displaced fluids. Or maybe you heard he's the guy that's quoted about, give me a long enough lever and a place to stand and I can move the earth. So that guy, right? Very famous, very brilliant guy. Another use here of one of the Archimedes solids, the truncated icosahedron, very commonly used. That is the classic black and white soccer ball shape. You probably recognized it. As well as the carbon-60 molecule, affectionately known as Buckminster fullerenes. Okay? We put a bunch of carbon atoms into that same configuration, and this forms the basic component of carbon nanotubes. Okay? Relatively modern, new material on the uprise, right? Super strong and super lightweight. Right? As soon as we figure out a way to mass manufacture it, we'll have indestructible clothing woven out of this stuff. It'll be great. But all based on this Archimedean solid shape. Okay? So there you go. That's it. That's the whole presentation. I'm done. There's an example. That's all you guys need to put together. Okay? So remember, that is your final goal for Friday, is to have that. Okay? For today, you need, by the end of today, right, you need to add on to your assignment post from Monday. That's due Wednesday morning. Put on a copy of your presentation so far. So at the end of the day, either at the end of class or if you decide to work outside of class, whenever you guys say that you're finished, everybody make a copy of it. So everybody turns in the copy and everybody turns in a copy of a document to-do list that says who is going to do what. So-and-so will finish this slide, so-and-so will add the pictures to that one, right? Whatever is left to do, you know exactly whose job it is, okay? Any questions there? No? All right, then. Everybody's got their topic. I think you got started, so let me start putting you into the breakout rooms here. And Lewis, and then for 2, Glenn, Marshall, and Angel, and Andre Leo, and let's see, in the last one. There we go. All right. There you go. Breakout rooms are open. Have at it. Get stuff done. Message me if you have any questions.